So this week we're going to discuss these two great results in Riemann paper, 1859. And the first one is the analytic continuation and the functional equation of the zeta function. And in fact, we're going to do these Dirichlet-Gauss functions. And the second is the zeros. And critical strip. So we call that the zeta function, as we've defined it, is meromorphic for real s greater than 1. But Riemann showed that the zeta s has a meromorphic continuation to all s in the complex numbers, and the only pole is at s equal 1. So everywhere else it's holomorphic. A slightly more symmetric statement, which is what he really proves, is that if you define a new function by multiplying this by a factor pi to the minus s over 2, gamma of s over 2, where this is Euler's gamma function, zeta of s. And this should be thought of as some kind of Euler factor at infinity, just as zeta was a product over primes. So the gamma function is regular for s bigger, the real part of s bigger than 0, and this is regular everywhere. It's an exponential function. So this is certainly meromorphic for real s greater than 0. What we proved, and he proves that this is meromorphic in the entire plane, and the only poles are at s equals 0 and s equal 1, which means since this has poles at all the negative even integers, this must have zeros at the negative even integers, which is the case. And he proves that this is equal to the same value at 1 minus s. So that's the famous functional equation, which only makes sense once you've made an analytic continuation, because if the real part of s is greater than 1, then here the real part of s is less than 0. And I'm going to show you his method, but I'm not going to do it for the zeta function because there's a slight complication that is caused by the poles, which I'll show you where that occurs. So we'll do the functional equation, and the continuation will do functional equation for L chi s when two things are the case. Chi is not the trivial character, so conductor, so a character of Z mod f star with f bigger than 1. So it's a character mod f, but f is bigger than 1, and we'll assume chi of minus 1 is equal to plus 1. That's certainly true for the trivial character, but you get other such characters. And then the functional equation is a little bit more complicated, but you're going to see that the proof is a little easier. You again multiply the function by this factor. So you can call lambda chi s the same factor, pi to the minus s over 2, gamma of s over 2. And then times L chi s. So again, this is a product over all the valuations of the rational numbers, because this is a product over all primes, and this can be considered the factor at infinity, which it is when we're going to get the Tate's thesis. Okay, so that's the case, and then we're going to prove that this has a holomorphic continuation to all s in C. This we knew already was holomorphic for s bigger than 0. This is, again, holomorphic for s bigger than 0. So again, the poles of this at negative integers imply that this function vanishes at all negative even integers. This product is holomorphic. Holomorphic continuation of all s in C, and it satisfies the functional equation, which isn't quite this easy. It's that this is equal to a certain constant, which I'll call W chi, and I'll tell you what it is, times the conductor to the 1/2 minus s. You didn't see that here because the conductor was 1, times the same function, but not at chi, and chi bar at 1 minus s, so you get the conjugate character. And chi is a real character, you get the same thing. Where w chi is the ratio of the Gauss sum associated to chi divided by the square root of f, and that's of absolute value 1, because in fact, in this case, g of chi times g of chi bar is equal to f. Not because chi of minus 1 is plus 1, you don't get a sign here. And so if you did this, okay, so that's what we're going to prove. People sometimes write it in the following way, the functional equation. I like it this way because you just have all the different Euler factors, and then you have a term here, which is a power of the conductor, and then a complex number of absolute value 1. So absolute value w chi is equal to 1, and in fact w chi times w chi bar is equal to 1. The complex conjugate. But some people like to simplify it and to pull this fact power of f into the definition of the thing. So some people like to do this. They call it c of s is f to the s over 2 times lambda of s. If you do that, then the functional equation looks a little simpler. Well, let's call that, this is chi s. You multiply this lambda chi s by f to the s over 2. Then the functional equation looks like c of chi s is just w chi times c of chi bar at 1 minus s. And that's what I'm going to prove. So in other words, you just, instead of multiplying the L function by this sort of modified gamma function, you multiply it by the modified gamma function and by this power of the conductor, another exponential function, which is non-zero everywhere. And then you get this functional equation where this thing just has absolute value 1 and is given by this formula. And that's equivalent to this, because you see, if I if I multiply this by f to the s over 2, then I have to do the same thing here with c bar. So I get f to the 1 minus s over 2, and that turns out to be exactly this factor of 1/2 minus s when you move them both over to that side. Anyhow, that's what I'm going to prove. And you'll see where this condition comes in the proof, and you'll also see in a certain key point where this comes in. And as I say, it's easier to do an analytic continuation if you don't have any poles, and this function will have poles at s equals 0 and s equals 1, so it's a little easier to take a non-trivial character. Okay, so that's what I'm going to do. So as I say, these are all proved. All the functional equation proofs that we have are by using Fourier analysis and Poisson summation formula. Riemann's original proof was that way, and then the generalization of Dirichlet-L functions was that way, and then Hecke's generalization and Tate's generalization all use the same thing. So let me just recall a little bit about Fourier duality. So we get back to last week. So last week we showed that the dual of R as an additive group is R by giving a pairing xy from R cross R by additive pairing into the circle, which is just e to the 2 pi I xy. That's additive in the first variable when y is fixed, and additive in the second variable when x is fixed. So it identifies R with its Fourier dual, which are the continuous homomorphisms from R to S1. And so if you have a function on the reals, I think I called it G last time, from R to C, and it has sufficient decline so that you can integrate it against characters, then you define the Fourier transform at a variable y is the integral over R. So that's the integral from minus infinity to infinity. That's why the function has to grow slowly at the boundary points. Well, it's g of x times the pairing of x with y bar dx. So this is g of x e to the minus 2 pi I xy dx. that defines a new function of y, because what this integral is depends on what y is. So for example, g hat of 0, the value of the Fourier transform at 0 is just the average value of g of x. Right? And these other, the values at y, you multiply g of x by that particular character that you get from y. You could call this psi y of x or something. That would be the character associated to y. You take the complex conjugate of that character and you integrate it and you see what you get. So a very famous function, which is at the base of all the functional equations, every single one of them is the function g of x is equal to e to the minus pi x squared. And the fundamental result is that it's equal to its Fourier transform. There are other functions that are equal to the Fourier transform. The Fourier transform by Fourier inversion is an operator which has order 4. So it has eigenvalues 1, I, minus 1, and minus I. And you can find all the eigenfunctions for the Fourier transform by taking this function and multiplying them by suitable polynomials that are called Hermite polynomials. So that's a beautiful theory, but we're not going to need any of those. We're just going to need this one function, which happens to be its own Fourier transform. So for example, it says that a particular example of this statement is that the average value of this function is 1, right? Because g of 0 is clearly 1, so that should be equal to g hat of 0, so that has to be equal to this, but it's much stronger than that. Okay, so I said that if you have one function g, you can make another function by doing various operations on the real numbers, like adding something to the argument or multiplying the argument by a scalar, and you want to see how that affects the Fourier transform. So starting with g, I'll define a new function, capital G, of w, depends on x and y, which are real numbers, and t, which is a positive real number. And it is, by definition, g of x plus w times t times the pairing of y with w. So what have I done? I've done translation on the real line by x. I've multiplied by a character depending on y, and I've scaled the argument by t. And I want to see how the Fourier transform depends on those operations. This is all put into one. Usually this is done 3 ways. You study how translation acts on the Fourier transform, how scaling by a character, and how multiplication does. But we'll do it all at once. Okay. So let's see if I can do this. Okay, let's calculate g hat. G hat is going to be a function of u. So it's the integral of this, right? It's the integral over r of this function, g of x plus w times t. Remember, x, t, and y are fixed times y, w. And then I have to take the pairing of w and u. So I'll uw bar, and then I'm integrating against w. Okay, so remember that x and t and y are just fixed constants here. The variables are u and w. Okay, so I'm going to rewrite this and do a change in variable and see if I can calculate this integral. So first thing is I realize that since I'm pairing both of these against w, this is y minus u paired with w, right? Because minus uw is uw bar. Except I'm not going to write it like that. Sorry. I'm going to write it as u minus y paired with w bar. Okay? Because y paired with w is the conjugate of w paired with minus y by the definition of this pairing, right? xy bar is the same as the pairing of x with minus y. Okay. Now, make the substitution. Z is x plus w times t. And consequently w, if I solve for w in terms of, it's z over t minus x. And dw is therefore dz over d. Remember, t is just a constant, x is just a constant, so I calculate the derivative, and I just did that. Okay, so let's rewrite this now in terms of a function of g. So this is equal to the integral over r. This, as w runs through the reals and x and t are fixed, z runs through the real numbers in the same orientation because t was positive. G of z. And then what do I have here? I have the inner product of u minus y with w, but I solve for w that way, so I have u minus y, z over t minus x bar, and dw is dz over t. I think I'm going to have to erase this or else I'm going to get into trouble. We'll come back to the functional equation. Okay, now let's multiply this all out and remember what's a constant and what's being integrated. The only variable is this z. Everything else is a constant. So for example, I can pull out x, y bar, right, in this thing. This is a pairing, so I mean it's bilinear in both arguments. So I get x, y bar. What else can I pull out? I can pull out this t divided by t. I can pull out u minus x bar, which is a ux. And then I have the integral of g of z. And then I just have the pairing of z with what? Well, u minus y over t. Or dz. Okay. Well, this is just, this itself is a Fourier transform. This is equal to x, y bar over t ux right? Oh yeah, right, ux, and then g hat of u minus y over t. Because this is just the Fourier transform of g against the character, evaluated on the character u minus y over t. So that's the formula for g hat of u. So let's see what's happened. We've multiplied it by a character, depending on x and y. We've scaled the variable, but now instead of translating by positive x, we've translated by minus y, and instead of multiplying by t, we've divided by t. Okay? Okay, so let's see what happens now if we apply Poisson summation. Poisson summation says if we have a function that has sufficient decay so that we can sum its values over all the integers, then these are the same as the values of its Fourier transform. Okay, so what happens if we do that? Here we have g, and here we have g hat. All right. So it says, let me write it this way. G hat of n is equal to xy bar over t, because that has nothing to do with where we're evaluating it. That just depends on x and y. And then we have if we call, I want to do this. Let's call theta of g of x, y, t, I think I did this last time, to be the sum of this function over the integers. Okay, so what are we summing here? We're summing the value of, now, this function over the integers. So I claim that that's equal to theta of the function g hat, t inverse minus y, minus yx, t inverse. because, and so that's equal to theta of g, x, y, t. And so you get a very general functional equation. Anytime you have a function g where you can make these sums, you take a bigger function by translating and multiplying it by characters, etc. You calculate the Fourier transform of that. It's also given by a translation and multiplication, but the multiplication is now by t inverse. And instead of multiplying it by the character uy, you multiply the character ux, and instead of translating by x, you translate by minus y. So it's a very general functional equation, which is this. Now, if you take a really simple function like this, which is equal to its Fourier transform, and you take this in the special case where x is equal to y is equal to 0, and let's take it in the special case where t squared is u, so u is the square root of t, it'll be a little clearer in that case, then what is theta g of x, y, t in this case? Okay, well, I'm not translating by anything, I'm just multiplying by t, so it's g of tw, and then this is the trivial thing because y is equal to 0, and then I sum that over the integers. Well, t is the square, so this, and I'm plugging into this function, right? So this is just the sum over the integers of e to the minus pi n squared u, right? Because the function is e to the minus pi n t. So you get n squared, t squared, and t squared I said was u. So that's the classical Jacobi theta function. And if I calculate theta of g hat, this is the trivial thing over t. T is the square root, t is square root of u. So this says that this theta function is equal to 1 over the square root of u, the same sum over n and z. But now I have x and y are 0, but I have a t inverse. So I get e to the minus pi n squared over u. And this is the famous functional equation of Jacobi's theta function. So this was known in Riemann's time. Jacobi had studied this function, and it proved that its value, so this, call this thing theta of u, that series. Jacobi had proved that it satisfied the functional equation that theta of u was 1 over the square root of u, theta of 1 over u. It's the famous modular equation of the Jacobi theta function. And Riemann took this functional equation and turned it into the functional equation of the zeta function. That was all he needed. This specific example of Poisson summation, where we didn't need the x and the y at all. We could have skipped them. You need this level of generality, as we're going to see when we get to the Dirichlet-L functions. Anyhow, it's a cute thing because if you've ever studied theta functions, from the point of view of representation theory, you know that they're related to a specific representation of the double cover of the group SL2. And this little operation that takes xy to minus yx is basically the matrix that looks like this in SL2, which has order 4. It's related to Fourier transform in what's called the Bay representation. So this general formulation is a pretty good one anyhow. But in any case, we only need it for the zeta function in this really, really special case. And then it just becomes this identity. Okay, so that's the basics that we're going to need from Fourier analysis. And as I say, every proof needs some of this. Tate does abstract Fourier analysis on locally compact groups, not just the real numbers, but Tate does Fourier analysis on things like the p-adic numbers, and then he does Fourier analysis on the Adels. We'll get to that. We'll get to all that. Okay, so here we go with the functional equation. So I need a little bit more background, which again was known to Riemann because he had read the work of Euler. We need a little bit more on the gamma function. So the gamma function, remember, is defined as the integral of u to the s e to the minus u over u. And we have to think a little bit about the convergence of this. So it's an indefinite integral, so you have to see what happens as u goes to infinity and u goes to 0. As u goes to infinity, there's no problem for any value of s. Because the exponential function decays faster than any polynomial. The absolute value of this is basically u to the real part of this. Okay? But no matter what value of s we choose, this is a well-convergent integral as we go to infinity. So if we integrate it from 1 to infinity, no problem. The problem is going to 0. As we let u go to 0, this function approaches 1. So we're basically integrating u to the s minus 1 du. And that's what the integral is approximating, right? And that integral is basically u to the s over s. And so it acquires a pole as s goes to 0. So the integral as u goes to 0 is good for real part of s greater than 0, but it acquires a problem at s equals 0. And in fact, the gamma function has a pole at s equals 0. And it's regular, non-zero for the real part of s greater than 0. And Euler really only needed it on the real line because he proved by integration by parts that gamma of s plus 1 was s times gamma of s. And since gamma of 1, you check is 1, because if you take s equal 1, this cancels out of this, and it's just the integral of e to the minus u. That allowed Euler to conclude that gamma of n was n minus 1 factorial. And for him, that was a good thing because he found a nice function of a real variable that interpolated n factorial. But Euler also used this to define the gamma function for negative values of s, because if you already had it defined in the half plane where real part of s was 0, it had a pole here, but if you wanted it from minus 1 to 0, you simply took the value s plus 1 and you divided it by gamma of s. So here you use that gamma of s is gamma of s plus 1 divided by s. And gamma of s plus 1 makes sense, so divided by s, you get it now defined in here. But that creates a pole at s equal minus 1, and then you do it from minus 2 to minus 1 using the same thing because you now have it defined here. You extend it this way, but that creates a pole at minus 2. And so you find it has a simple pole at s equals 0, minus 1, minus 2, all the way down. And it's easy to calculate what the residue is. The residue is at s equal minus n, if I got it right, is minus 1 to the n times n factorial. Yeah, I think that's right. Okay, and Euler made one more observation, which is going to be helpful to us. And that is that if you multiply gamma of s times gamma of 1 minus s, you found a function that now had a simple pole at all integers. Right? I mean, this has a pole to negative integers, therefore this has poles at all the positive integers. And you knew a function that had a simple pole at all integers. Namely, if you took the function of any constant over the sine of pi s, has the same property, because this now has whenever this is 0, that would work. And Euler proved by calculating the limiting value of this at one point that the constant was pi. And he proved this identity, which is sometimes called the duplication formula. And from that formula, he took s equal a half to conclude that gamma of 1/2 squared was equal to pi, because the sine of pi over 2 is 1. And consequently, since this is a positive number, the gamma of 1/2 is the positive square root of pi. And that allowed him not only to develop the values of the gamma function at integers and its residue at none, but he gets the value at all half integers too. Okay, so that's what we're going to need about the gamma function. So now what we do, and that was, is we produce the function n to the minus s, which we're going to have to sum in all of these Dirichlet series out of the gamma integral. So let v, so here's the gamma integral, let v be equal to pi n squared u divided by f. Remember, this chi is of conductor f. So Riemann did the same thing when we took f equal to 1. Okay, so let's calculate v to the s over 2 power, because we're going to want to do gamma of s over 2. So gamma of s over 2 is the same integral with u to the s over 2 here, right? Okay, so what is v to the s over 2? Well, it's pi to the s over 2. That's good. That's appearing in this functional equation. N squared to the s over 2 is n to the s, right? Right? Yeah, right, exactly. And then I get f to the minus s over 2, because this is in the denominator, times u to the s over 2. Okay? Good. So then let's take this gamma integral and substitute in for u this, let's consider the following integral. Of, u to the s over 2, e to the minus pi n squared u divided by f du over u. Okay. Now this u to the s over 2, I'm going to write as v to the s over 2, and I'm going to invert this. So that's equal to the integral from 0 to infinity of v to the s over 2 times the quantity pi to the minus s over 2, n to the minus s, f to the s over 2. Those are just constants, right? And then I have this, and notice that this is e to the minus v, right? E to the minus v. And since u and v are constant multiples of each other, du over u is the same as dv over v. Good. So what do I have here? I have the gamma integral for v at s over 2 times the constant. Pull the constant out. So this is now pi to the minus s over 2. The gamma integral I'll write as gamma of s over 2. F to the s over 2 times n to the minus s. Okay. This is the factor. I hope I did this right. Good. Yeah, right, exactly. Okay. Okay, now I want to take the sum of this over the positive values of n. And this integral, by the way, this all makes sense for the real part of s greater than 0. But if I want to get L chi s, if I want to get f to the s over 2, pi to the minus s over 2, gamma of s over 2, L chi s, I have to take this expression and sum it over the positive integers with the factor of chi. So for each integer, it's equal to this integral, and that sum of chi of n to the minus s is absolutely convergent for the real part of s greater than 1. So I can exchange the integral of the sum, and I get this is equal to the integral from 0 to infinity of u to the s over 2 times the sum from n greater than or equal to 1 of chi of n e to the, where is it, minus pi n squared u over f du over u. And now that only makes sense for a real part of s greater than 1 because I've used the fact that I've switched the integral and the sum. So for each term in this, I got an expression. For each term in the sum, I got an expression in terms of this integral. I sum this up over the positive integers with the factor chi in. So I sum these integrals up over the positive integers with the factor chi put in, and then I rearrange that to be, instead of the sum of the integrals, the integral where I put the sum inside. And I'm getting something that's beginning to look like my theta function. But the problem is that I've summed here over the positive integers, which is what you do to define the L function. However, notice that this is the same for a positive integer and for a negative integer, because I have the n squared there. And this, miraculously, well, this would be n prime to f, right? Equal 1. But I can define this to be 0 for n not prime to f. I get the same answer. And moreover, I've assumed that chi of minus 1 is equal to minus 1, is equal to plus 1. So I can extend chi to the negative integers by saying chi of minus n is equal to chi of n. Right? So that this sum now becomes 1/2 the sum over all integers of chi of n, and that's where I've used evenness of the character. So you see the proof has to be different when the character is odd. Okay, and let's call this thing in the middle here theta chi of u. Because it's exactly this, this Jacobi's theta function if chi were the trivial character and f was 1. And it's just a modification of that. You know, where I've summed over the integers, it looks very Poisson summation-like. And I get a theta function du over u. And that integral, as I say, converges for real part of s greater than 1. Okay, now here's another thing that's very nice. When the character is non-trivial, chi of 0 is equal to 0. See, that's not going to be true for the Riemann zeta function when you extend the character. And consequently, this function now has exponential decay, right, as u goes to infinity, because there is no constant term here where you just get the constant function 1. All of these functions have exponential decay. So, Riemann writes the integral from 0 to infinity as the integral from 1 to infinity, 0 to 1 of u to the s over 2, theta chi of u over u, plus the integral from 1 to infinity of u to the s over 2, theta chi of u du over u. And he observes that this makes sense for all s, because this function has exponential decay, and so it decays faster than any power of u, just like the gamma function. That's why it's critical that we take a non-trivial character so that we don't have the term n equals 0 here. Okay, but this doesn't make any sense as s is, unless s is bigger than 1, because as we saw already, if we let s tend to 0, these terms would just be, then this behaves like the exponential function, and again, we can't make it. Okay, but now he uses Poisson summation. In the form that I gave you, and I leave it as an exercise for you guys to prove the following, to show that G of chi bar times theta chi of u is equal to the square root of f over u theta chi bar of u inverse. So this is a generalization of the Jacobi theta identity, which is the case where chi is the trivial character. But again, you have to apply this to the correct function little g and the correct values of x and y and t. And I'm going to leave that to you. But this is the functional equation of the generalized theta function. And so he substitutes that in to this part of the integral, which this again converges for real s greater than 1. He substitutes that in. Okay, let's do it. So we find that this multiple of the L function is given by two integrals. First of all, it's the integral from 1 to infinity, which we saw made sense of u to the s over 2, u du over u, plus the integral from 0 to 1. Now we make the change of variable. U goes to u inverse. And that becomes the integral from 1 to infinity of u to the minus s over 2, theta pi chi of u inverse. And again, you get du over u. Maybe you get a minus sign. I'm not 100% sure here, but all right. So again, this has just as many problems as u goes to infinity as the original integral had when u went to 0. But we now use this functional equation. I'll write it like this. And finds that theta chi of u inverse is g of chi, let's see if I get this right, the square root of u over f, theta chi bar of u. So that's the key step that's done by Poisson summation. And I hope I did this right. So if I put a u inverse here, well, let's put a bar here, and then this becomes g of chi, square root of f over u, theta chi of u inverse. Yeah, I think that's right. Okay, and he rewrites this as, and he rewrites this as now g of chi over the square root of f. And what power of u do we have? This is the integral from 1 to infinity. The power of u is u to the 1/2 minus s over 2. So the u to the 1 minus s over 2. And then we have the chi bar of u du over u. And this is again now exponentially decreasing as u went to infinity. So this integral now makes sense for all s. And so he's written this product of the Dirichlet-L function by this exponential factor as a sum of two integrals. The first one makes sense for all s, and the second one now makes sense for all s. And so he has a holomorphic continuation to the entire s plane. And if you look at this, when you substitute you substitute 1 minus s for s, you essentially switch the roles of these two integrals. And that's the functional equation. I mean, the s over 2 gets replaced by u to the 1 minus s over 2, du over u stays the same, and this becomes that. So I'll leave that to you. I'll let you finish the functional equation. So again, I've done this in a very sketchy way, but the argument is always the same. You obtain First, you have to obtain an integral expression for the L function, or the L function multiplied by a certain factor. So it's the integral, like a gamma integral, but instead of just putting in one exponential factor, you have a sum of them, which becomes a theta function. You prove a functional equation for the theta function by Poisson summation, which in this case is this. You rewrite the integral from 0 to infinity as from 0 to 1 to 1 to infinity, and you transform the integral from 0 to 1 to an integral from 1 to infinity using the u goes to u inverse. Then you rewrite this function in terms of the functional equation of the theta function in this way, and then you obtain the functional equation. Truly amazing argument, and it gets more and more and more elaborate the more functions you want to do it for. And this is already bad enough. I want to emphasize that at the very end of this, you have to use the fact that g of chi times g of chi bar is equal to f. To get the full functional equation, you need that, or equivalently, that this thing has absolute value 1. So we not only are using Fourier analysis on R, and really on R mod z, because we use the Poisson summation formula, but we're using Fourier analysis on z mod fz for characters chi of z mod f star. And what we're going to do further on is we're going to combine the Fourier analysis here and the Fourier analysis here to be Fourier analysis on the L's. That's the big idea. It's not to break it up into just real analysis and analysis on a finite abelian group, but analysis on some locally compact abelian group that contains both of them. That's a much more symmetric way of doing it. Because this becomes more and more complicated. When you do it, when you try to prove the same thing for the zeta function of a number field, first of all, the for zeta k of s, the real analysis now takes place on R tensor, the ring of integers, modulo the ring of integers. And this isn't even a self-dual lattice in here yet. It brings in the inverse difference. So this isn't quite as simple as R mod z. But in any case, this is, R to the n modulo a lattice. And then the finite Fourier analysis takes place on A mod f for certain characters of A mod f star. So that becomes quite complicated because you're first of all doing Fourier analysis in n different variables as you do these integrals. So you need theta functions of many variables, and then you have a much more complicated finite ring to work with. So we're going to try to package that instead by introducing this wonderful concept of the Adels. And I'll do you at least an introduction in Tate's thesis where he does this proof. A very nice paper, by the way, would be to do the functional equation for the Dirichlet-L functions precisely, proving this law for the theta function, doing the case of odd characters, and doing the correction that you have to do. What you have to do in the case of the trivial character is you write this sum as the sum over n not equal to 0, and then the term at n equals 0. And you have to subtract off that term, and that's exactly what leads to the pole and the calculation of its residue and things of that nature. Well, since we have a little time left, let's go back to what we proved about the L functions at 1. So remember, recall that we had formulas for L chi at 1. And they broke up as to whether it was a real character or an imaginary character. So the imaginary character looked like minus pi over the square root of f times the sum of chi bar of b times b over f, from b is equal to 1 to f. That's if chi of minus 1 is minus 1. And for the real character, it was, well, there wasn't a pi anymore. It was something like 1 over the square root of f. I'm guessing here. B is equal to 1 to f of chi bar of b log of the absolute value of 1 minus e to the 2 pi I b over f. Something of that nature. right? So those look completely different at 1. But now we have a functional equation. And remember, in the functional equation, in this case, in the odd case, we have this factor pi to the minus s plus 1 over 2, gamma of s plus 1 over 2. And in this case, we have the factor pi to the minus s over 2, gamma of s over 2. So now we look and see what happens at s equals 0, because in this s goes to 1 minus s, 1 goes to 0. What's happening at 0? Okay, this function is regular at s equals 0. I mean, we have gamma of a half, which we know is the square root of pi. This is also gamma of minus a half, so that this function is just 1 at s equals 0. But this function has a pole at s equals 0. Okay, and therefore, the corresponding L function, which is symmetric at s equals 0 and s equals 1, has to have a 0 at s equals 0. And when you go through dividing by the conductor and everything like that, you find the formulas that L of chi of 0 is much simpler than the formula was at 1. First of all, chi bar is replaced by chi, which is already better, right? So this becomes something like, up to constants and whatever, minus the sum b is equal to 1f chi of b times b over f. Namely, this is an algebraic number. I mean, this is not an algebraic number, and that's a square root, but this is an algebraic number which is in the field generated by these roots of unity. So, for example, if chi is a quadratic character, this is a rational number. Okay, and that's in the odd case, and in the even case, you get the derivative at 0. And it turns out to be something like minus 1/2 the sum from b is equal to 1 to f of chi of b. Again, you replace chi by chi bar, the log of 1 minus e of 2 pi I b over f. Okay, let's call this thing zeta to the b, 1 minus zeta to the b, because that's what it is. And let's rewrite this a little differently. Suppose I wrote it as the log of the absolute value of the product of 1 minus zeta to the b to the chi of b. Now you can't really do that because you can't take a complex number to a complex power. You could do this if this were a quadratic character, b plus or minus 1, but let's at least pretend. And let's call this thing epsilon chi. Well, what is that? That's the projection of a unit in the cyclotomic field into a certain eigenspace for the Galois group action, into the chi eigenspace for the Galois group action. And it's if you look at the action in the cyclotomic field of F roots of unity of this Galois group, this acts on the units. And you get non-trivial eigenspaces on, say, this complex vector space for the characters chi which are not equal to 1, which are even characters. Remember, the rank of this group is R1 plus R2 minus 1, and this R1 is 0, it's a totally complex field. R2 is half the dimension, so it's R2 minus 1. That's the number of even characters. And every even character has a one-dimensional eigenspace for the Galois group on this, and this is a generator of it. Okay. Whereas for odd characters, the eigenspace for the units is trivial. So look at what's happening here. First of all, the order of vanishing of this L function at 0 is the rank of that chi eigenspace of the units. Just like for the zeta function, the order of vanishing was the rank of the unit group. And the leading term is the logarithm of a unit in that eigenspace. Well, that's a little wrong here. I mean, there is no unit in the eigenspace. But here, when we have a rank 1 unit, we're getting a determinant of a 1-by-1 matrix. Namely, we're just getting the log of a unit. And this was Stark's great idea that, remember, the zeta function here is a product of all these L functions. And he thought that the regulator should somehow decompose as a product of regulators where when you decompose the unit group into eigenspaces for the Galois group. And the order of vanishing of the L function should tell you what the rank of that eigenspace is. In this case, the rank is 0. In this case, the rank is 1. And so, first of all, it's a much cleaner formula, but you also get this order of vanishing is right. So we're going to come back to that when we have Artinel functions, and we'll make Stark's conjecture and things like that. But this was the beginning of it all. Namely, you needed the functional equation to really see what the meaning was of these formulas of Dirichlet at s equal 1. You know, why was this one so much simpler than this one? Because this one was really a formula for the first derivative at s equals 0. And this one was a formula for the value at s equals 0, which is much easier. Okay? And as far as the first derivative of this at s equals 0, we know very little about it. Because it's not the leading term. See here, the value is 0. Because it has to vanish to order 1 for the functional equation to work. Okay? So the functional equation allows us to transform some of our explicit formulas to explicit formulas at the reflection point where they're easier. And it always turns out to be easier to study things at the negative integers. So for example, Euler's formulas that, you know, zeta of 2k is equal to a rational number times pi to the 2k, he couldn't figure out what zeta of 2k plus 1 was. He did a lot of computation. He makes a comment in one of the papers that you shouldn't expect a formula like this, which means that he spent hundreds of hours trying to check if it was true. But, you know, what was the mystery? Well, the mystery is that zeta of 1 minus 2k is equal to essentially this rational number. I mean, there are some things that come in the functional equation, but it's, and zeta of 1 minus an odd number, 2k plus 1, which is a negative integer, is equal to 0. And so what was mysterious about this is it's related to the first derivative at these points by the functional equation. And the first derivative is much more complicated than a rational number. I mean, like this. And we now know that it's related to regulators in higher K theory, whatever that means. That's a generalization of regulators on the unit group. The unit group is K1 of the ring of integers. So that was, I mean, you could say we know more than Euler, except that we don't know anything about regulators in higher K theory, so it's a theoretical advance of not much great use. Okay, but this is just one way that the functional equation plays a huge role. And another way, as we're going to see as we move on to L functions of elliptic curves and things like that, is it says that the terms in this Euler product are not random things. You know, that they're all related to each other, or otherwise you wouldn't have any continuation. I mean, I could make an Euler product that converge by taking chi of p to be anything of absolute value 1, right? I mean, I could certainly define the product over all primes p of 1 minus chi of p, p to the minus s, inverse, let's call it f of p, right? It could be multiplicative, it could be all kinds of things, but it might not be periodic mod n, mod anything. And I'd have this perfectly well defined for real part of s greater than 1, it just wouldn't have any continuation anywhere. And to say that you have an analytic continuation functional equation is basically that these things are all related to each other, and in this case it means that they're periodic mod n from a character mod n. Okay, we'll resume on Thursday with a little bit about the zeros of the zeta function, and then we're going to go on to number fields and L's, things like that. We'll go into the 21st century.
What?
So I want to advertise again, a little early, the seminar talk this week. It's by a friend of mine, Jeremy Boer, who's a very good speaker, so he'll give a pre-talk too and a talk. So you guys want to know that.